welcome to this lecture. In today's subscriber requested lecture, we're going to be doing excitability. So let's get started. So, excitability is very easy to understand. It's the distance between the threshold and resting membrane potential, okay? So you could see the membrane potential graph here. There's the threshold and resting membrane potential. Excitability is determined by the distance between the threshold and resting membrane potential, okay? So if the threshold suppose is higher, if the greater the distance between the threshold and resting membrane potential, the less excitable the cell is, okay? I'll explain why. The lesser the distance between the thresholds and resting membrane potential, the greater the excitable the cell is, okay? So why is that? Now, in our action potential lecture, we know that for a cell to be depolarized, it must reach the threshold. The membrane potential must reach the threshold. And how does it reach the threshold? It reaches by the ligand-gated channels. They open, right? And that small influx of sodium ions goes into the cell, right? There's a small influx of sodium ions. And that basically makes the cell more negative or causes that small depolarization. And once it hits the threshold, it will cause the upstroke, right? So, if the distance between the resting membrane potential and the threshold becomes smaller, if it becomes smaller, meaning in this example, the threshold is lower, right? Meaning it does not require as much of sodium ions to reach the threshold, right? So that means it's more excitable, okay? So that means a small signal can depolarize or cause an upstroke of that cell, okay? Suppose the threshold is higher, somewhere here, okay? Suppose the threshold is higher. The distance between the resting membrane potential and the threshold has increased, right? Meaning, to depolarize that cell, to cause that depolarization of that cell when the threshold is higher, it requires more sodium ions to reach the threshold, right? Meaning it's less excitable, okay? So I wrote it here that the lower the distance between the threshold and resting membrane potential, the greater the excitable the cell is, okay? The greater the distance, suppose is here, the greater the distance, the lower the excitability of the cell, okay? So I hope you understood what excitability is. Very, very easy. Now, what are some factors that can determine this excitability? We'll go through it. There's two things. There's potassium ions and there's calcium ions. So potassium ions can affect the resting membrane potential and calcium ions can affect the threshold, okay? It's easy to understand that why potassium ions control the resting membrane potential, because if we look again in our action potential lecture, we know that for after the cell has repolarized and it enters hyperpolarization, why does it enter? Because as I said in our lecture, there's a lag that in this area, the voltage gated potassium ion channels, they don't close, right? Now, how does it reach back into resting membrane potential? Remember, I said in this lecture that it reaches through potassium leak channels, right? Potassium ions, they diffuse into the cell, and that's how it reaches back into resting membrane potential, right? If potassium ions, they influx, meaning there's an movement of positive ions from outside to inside of the cell. If there's an influx of potassium ions, it would become more positive, right? The cell would become more positive. That's how it reaches from hyperpolarization to resting membrane potential. So that means potassium ions control the resting membrane potential, okay? We'll explain why calcium ions control the threshold, but first, let's go through how potassium ions concentration inside and outside of the cell affects resting membrane potential. Now, as I said, potassium ions affect the resting membrane potential, right? Let's see how. Suppose there is a cell where there's potassium ions inside and outside, okay? and it's equal. The concentration between inside and outside of the cell is equal. So there's no transport in or out for the potassium ions. Suppose we decrease the concentration of potassium ions outside of the cell, okay? We decrease the concentration, meaning there is more of potassium ions inside the cell, right? Meaning there is a greater concentration in, so it would diffuse out, right? That's how diffusion works, simple diffusion. Or in this case, it's facilitated diffusion because these are ions. Ions directly cannot pass through the phospholipid bilayer. Do you remember? In this case, it's facilitated diffusion through the ion channels, right? So it would diffuse out of the cell from higher to lower concentration. That means once it diffuses out, remember again in the action potential lecture, we talked about electrical gradient. That means if these potassium ions, they leave the cell, inside of the cell would become more negative, right? Inside of the cell would become more negative. So the membrane potential of the cell, it becomes more negative. So I can draw the line here that if the potassium ions concentration outside of the cell decreases, the resting membrane potential would become more negative because potassium ions diffuse out, and inside of the cell, because of that diffusion, but positive ions are leaving the cell, meaning inside of the cell becomes more negative. So the resting membrane potential becomes more negative, okay? So that was for potassium ions concentration outside of the cell decreasing, okay? That's a condition called hypokalemia, okay? You could research it. That basically means the concentration of potassium ions in the blood decreases, okay? Now, let's look at the opposite effect. Again, if the potassium ions concentration is equal outside and inside, it won't diffuse. There's no diffusion, right? And that is the resting membrane potential. Now, suppose the potassium ion concentration in the blood increases, okay? This condition is called hyperkalemia, okay? This means that the potassium ions would diffuse into the cell, right? Making the cell more positive, meaning it makes the membrane potential or the resting membrane potential of the cell more positive. So it would move the resting membrane potential upwards, okay? So that means for here, potassium ions concentration increases, okay? Now, how does this affect excitability? As I said, excitability is the distance between threshold and resting membrane potential, right? If the potassium ion concentration outside of the cell decreases, that means potassium ions inside would diffuse out, right? Making the cell more negative. The resting membrane potential becomes more negative. So the distance between the threshold and the resting membrane potential, it increases, right? Making the cell less excitable because it requires more sodium ions to influx, as I said, to reach the threshold and cause that depolarization, right? If you increase the concentration of potassium ions outside of the cell, that means potassium ions would diffuse into the cell, right? Potassium ions would diffuse into the cell, making the cell more positive, meaning the resting membrane potential becomes more positive. So the distance between the threshold and the resting membrane potential, it becomes lesser. That means it's more excitable, okay? So that was for how potassium ions can affect the resting membrane potential and how it can affect excitability, okay? So very easy to understand, right? So let's move on to how calcium ions affects the threshold and subsequently affects the excitability. All right, so let's go through calcium ions. How does calcium ions affect the threshold? So we learned that in our action potential lecture, there are ligand-gated sodium ion channels, right? And these ligand-gated sodium ion channels allow sodium ions to enter the cell, causing that small depolarization to cause the upstroke or that greater depolarization. Now, around the outside of this ligand-gated sodium ion channels, around it, it attracts calcium ions. Okay, it attracts calcium ions. So calcium ions actually kind of block this ligand-gated sodium ion channels. Why can't these calcium ions enter the cell itself? And if it attracts, right, why can't it enter? Because these are ligand-gated sodium ion channels, and we know that ion channels, they're restricted to only one ion for this specific ion. So calcium ions can't enter. So even though it attracts, it just kind of blocks this. So this is how you could say that calcium ions regulate the transport of sodium ions into the cell. Now, suppose we decrease the calcium ion concentration outside of the cell. We decrease the calcium ion concentration outside of the cell, meaning the calcium ion concentration in the blood decreases, right? That condition is called hypocalcemia, okay? Don't confuse it with this one, which I said is hypokalemia, okay? This one is hypocalcemia. Now, we decrease the concentration of calcium ions outside of the cell. So we're decreasing it now. Now, this means that there will be less disturbance of sodium ions to enter the cell, right? Because both sodium and calcium ions, they are positively charged, so there will be repulsion as they're entering, right? So if the concentration of calcium ions is lower, that means that there will be less disturbance for sodium ions to enter the cell. That means that the cell would, it would easily be depolarized, right? So that would decrease the threshold. Why would it decrease the threshold? It would decrease the threshold because it makes the cell more excitable, right? Because more sodium ions can enter, it makes it more excitable, right? That means that the distance between the resting membrane potential and the threshold must decrease. So the threshold actually becomes lower, okay? The distance lower, meaning it's more excitable, right? Suppose we increase the concentration of the calcium ions outside of the cell. That condition is called hypercalcemia, okay? For potassium ions, if you increase the concentration of potassium ions in the blood, that is hyperkalemia, okay? So it's different, okay? So you increase the concentration of calcium ions. It's more than normal. So when a sodium ion would try to enter the ligand-gated sodium ion channels, it would have a lot of disturbance, right? It would repel, it would bounce around, and then finally enter, right? That means that less sodium ions enter the cell. That means that the cell is less excitable. What does it mean by a cell being less excitable? Less excitable, meaning the distance between the threshold and resting membrane potential is greater, right? So the threshold in this case would actually go above, okay, above the normal threshold. So it would go above the normal threshold. So I hope you understood. It's very easy to understand. For this case where the threshold would decrease, meaning it's closer to the resting membrane potential, right? Meaning it's greater, it's more excitable, right? That is when calcium ion concentration in the blood decreases, and when it's less excitable, meaning less sodium ions enter the cell, that's when calcium ion concentration in the blood, it increases, okay? It's very easy to remember both of these diagrams. You could say that first you just have to remember that calcium ions, they control the threshold, and potassium ions, they control the resting membrane potential, okay? So both of them, suppose calcium ions and potassium ions, they decrease, right? They both, for each one of them, they would bring down their respective line, okay? You can remember like that. So if potassium ions, they decrease, It's meaning that the resting membrane potential becomes more negative. If calcium ions decrease, the thresholds becomes more negative. Okay, if it increases, it pushes the graph up. For potassium ions is the resting membrane potential, right? It pushes it up, meaning it becomes more positive. It pushes it up, becomes more positive. For calcium ion, it affects the threshold, so that means it pushes the threshold up. It makes it more positive. So yeah, that's how I remember it, basically. How potassium ions and calcium ions, they affect how the graph is when they increase or decrease the concentration. So yeah, that was very easy to understand. Excitability is just the distance between the threshold and resting membrane potential. The greater the distance, the lower the excitable the cell is. The lower the distance, the greater the excitable the cell is. So we looked at how calcium ions and how potassium ions and calcium ions affect one, which is resting membrane potential or threshold. Remember, in this explanation, I used electrical gradient as the explanation, that when it diffuses in, the cell becomes more positive, and that's how resting membrane potential is increases or decreases. We can't use the same explanation in this, because in this there is both the sodium ion and the calcium ion, so they're two ions, so you can't really determine the electrical gradient. It would be different. In this case, there's only one ion, so electrical gradient depends only on one ion, so we can use that as an explanation. Whereas for this, we're changing the concentration of the calcium ions, and that affects the concentration of the sodium ions. They're two ions, so we can't use the explanation of electrical gradient in this. So yeah, I hope you understood excitability to the person who asked for this video. And if you have any questions, you could DM me to my Instagram page at dsr.manav, and I'll post these notes in the Google Drive photo link that I'll post it both in the description and the comment section. So yeah, I hope this lecture was helpful for anybody who's watching, and I hope you have a great day. Bye bye.